Hi, my name is Chongli Chen, and welcome to today's lecture on responsible innovation and artificial intelligence. So today's talk will be split into two parts. For the first part, I will be going over some of the research which has been done to ensure that the machine learning algorithms we develop satisfy desirable specifications, such that during deployment, it is safe, reliable, and trustworthy for use. In the second half, Yaslin will dive into further details of the ethical implication of machine learning algorithms, and more importantly, how we can be thinking about designing these algorithms and deploying these algorithms such that it is beneficial to society. So to start, I want to give a quick motivation into why we as machine learning researchers should be thinking about both research and our responsibilities. So with all of the great research which has happened over the past several decades, machine learning algorithms are becoming increasingly powerful. There has been a lot of breakthroughs in this field, and today I'll just mention a few. So one of the earlier breakthroughs was using convolutional neural networks to boost the accuracy of image classification. More recently, we now have generative models that is capable of generating images with high fidelity and realism. We've also seen breakthroughs in biology, where now machine learning algorithms is capable of generating or folding proteins to unprecedented level of accuracy. Indeed, the recent AlphaFold system won the last CASP competition, which is a protein folding competition on folding unknown protein structures, later crystallized for validation. We've also seen machine learning and reinforcement learning systems that is now capable of beating humans in games such as Go. And more recently, we've seen machine learning algorithms pushing the boundaries of language. With the recent GPT-2 and 3 models, we've seen that these models is not only capable of generating text, which is grammatically correct, but really demonstrated that they are grounded in the real world. So as the saying goes, with great power comes great responsibility. And I think now it is more important than ever for us to question what might be the negative impacts and risks of all of this. And more importantly, what can we do to mitigate for these risks? To highlight why we need to start thinking about these risks, I want to start with a few examples, starting with this one, which some of you are already maybe familiar with. So this is a paper published in 2013 titled Intriguing Properties of Neural Networks. They probably use the adjective intriguing because whatever it is that they have found in this paper was a little bit unexpected. So what did they find? Well, what they found is that you can take a state-of-the-art image classifier, like here, and you can give it an image like the one you see of a panda here. And indeed, this classifier can correctly predict this as a panda. So what happens now if I take the exact same image, add on the tiniest bit of perturbation to this image? So tiny that it is imperceptible to the human eye. And you can see this, that the left picture and the right picture looks almost exactly the same. In fact, they do look the same. So what happens now when you put this new image through this neural network? We would actually expect the output of the neural network to be the same. But rather, when you put this new image through this neural network, the network is now almost 100% confident that this is in fact a gibbon. So in this instance, maybe misclassifying a panda for a gibbon does not have too many consequences. But actually, we can choose the perturbation to make the output of the network to be whatever it is we want to be. We can change this to a bird, to a vehicle. If such a classifier was used for, say, an autonomous driving system, this can have catastrophic consequences. Some other machine learning failure modes might be slightly more subtle. There has been some studies on the recent GPT-2 model where they have shown that this model might be carrying some of the biases that exist in society today. So in this paper titled "The Woman Worked as a Babysitter on the Biases in Language Generation," What they did was a systematic study on how the model behaved conditioned on different demographic groups. For example, if the prompt was changed from the man worked as to the woman worked as, the subsequent generated text drastically changes in flavor and may be heavily prejudiced. Similarly to the black man worked as versus the white man worked as. And I want everyone to take a few seconds to read the generated text after we change the subject of the prompt. As you can see, even though this language is extremely powerful, it does carry some of the biases we have in society today. And if this is the model that is used for something, say, like auto-completion of text, it can further exacerbate and feed into the biases that we already have. Yason will go later into details of the ethical risks of how we can use machine learning, for example, using machine learning in surveillance systems or for weapons. So I think at this point, we should really be asking this question. What are our responsibilities as machine learning practitioners? So this is, of course, an open question, and possibly with no single right answer. But I see one of our responsibilities would be to ensure that the machine learning algorithms we deliver satisfy desirable specifications. In other words, we should have a level of quality control over these algorithms to enable their deployment to be safe, reliable, and trustworthy. And if we get this right, with this, we can bring many more opportunities, many more applications enabled. For example, more reliable and safe autonomous driving systems, more robust ways of forecasting weather for renewable energy, etc., etc. But for all of this to be possible, we really need to know how to stringently test for our machine learning algorithms. So how can we make sure that our machine learning algorithms are safe for deployment? Well, like how many other algorithms are quality controlled before deployment, we need to ensure that they satisfy desirable specifications. For example, for an image classifier, we want it to be robust to perturbations. If it's a dynamical systems predictor, we would like it to satisfy the laws of physics. We want it to be robust to feature changes that is irrelevant for prediction. For example, the color of the MNIST digit should not affect your digit classification. If we're training on sensitive data, it should be differentially private. If we're giving our neural network images out of distribution, our neural network should become more and more uncertain, not more and more certain. So these are just a few specifications that we would like our neural networks to ideally satisfy. But there are many more. So here I want to introduce the paradigm of specification-driven machine learning. So what do I mean by specification-driven machine learning? Well, we should realize the core issue lies when you're training with limited data, your model can learn a lot of spurious correlations to boost metrics, but has nothing to do with prediction. So unfortunately, what this means is that your model is ultimately hinged on the data and the metric. So unless you do your training carefully, your model can inherit a lot of undesirable properties that is in the data, unless you specify otherwise. So in this instance, if the data is biased and limited, then your model is to be biased and non-robust, unless we specify otherwise. So in specification-driven ML, we want to enforce the specifications that may or may not be present in the data, but essential for our systems to be reliable. So how we can enforce these specifications will be the subject of the rest of my talk. So I want to start with a specification that is relatively well studied and one which I have already kind of touched upon. That is the robustness of our neural network to perturbations or adversarial perturbations. So this specification is really essential if we want to deploy our networks to applications that require robustness or for applications that has real adversaries in the mix. So to formalize, I first want to reiterate what it is we want to achieve. So we want our image classifier's output to be unchanged under any additive imperceptible perturbations. So to define this more mathematically, let's start with a few notations. So here we denote the neural network as a function f. And this function takes in as inputs an image, which is your panda, otherwise denoted by x, parameters of your network denoted by theta, and the output of this neural network should be a probability vector over your labels, or more commonly, the logarithms of a probability vector, otherwise known as logits. So ideally, we would like our neural network's output to be exactly the same as the label. So in this case, it's what we know to be a panda, but we actually express this to be in a one-hot format vector, where the element corresponding to the label is 1, and elements corresponding to all other labels to be 0. So now we have our notation set out. Let's go straight into the specification. So this is the adversarial robustness specification. I know this is a lot to take in one page, so I will try to break this down a little bit. So firstly, we note that the delta here denotes the perturbation. And what this equality is simply saying is that we want the index of the maximum probability in the probability vector outputted by the neural network to be exactly where the 1 is in our one-hot vector. So this is a very convoluted way of saying we want our neural network's output to be correct, subject under this perturbation. And now the second line says we want this to be true for all perturbations within the set of imperceptible perturbations. So in practice, to ensure imperceptibility, we simply constrain the size of the perturbation under a certain norm ball to be less or equal to epsilon. So the norm ball normally considered is the L infinity norm. So now we have the specification designed. I want to go into a little bit more detail of one of the more commonly used methodologies to train our neural networks to satisfy this specification. And that is adversarial training. So adversarial training is very similar to standard image classification training, but with a tiny bit of a twist. So indeed, with standard image classification training, what ideally we would like to do is we want to optimize our network's weights such that the input image is correctly classified. So in this instance, you see the input image is a cat, and thus we want the output prediction of this neural network to be a cat as well. Algorithmically, what this means is that we want to minimize the weights of our network with respect to expected loss over our data. So the loss normally considered is the cross-entropy loss, and here capital D denotes our data. What this loss ensures is that our predicted probability vector to be as close as possible to the label. So now adversarial training does something very similar, except with the extra data augmentation step. So here, not only do we want the original image to be correctly labeled as a cat, we want the image now with any additive imperceptible perturbations to also be correctly labeled as a cat as well. So in practice, to iterate through all of the imperceptible perturbations is obviously computationally infeasible. So instead, what adversarial training tries to do is it tries to find the worst case perturbation. So what I mean here by the worst case perturbation is simply the perturbation that maximizes the difference between the prediction and the label. So I want to reiterate this again to make this a little bit clearer. We want to maximize the prediction, the difference between the prediction and the label with respect to the perturbation, which is actually image space, not in parameter space. So now, how does the objective of the adversarial training change? Well, this is now the objective of the adversarial training. And you can see that it differs slightly to before, where before it was just a minimization problem. Now this is a min-max problem. So first, we want to find the maximum of the loss with respect to delta, which is our perturbation. And note that this delta belongs in this set of perturbations denoted by capital B, which is the set of imperceptible perturbations. Then once we have computed this maximum, now we want to minimize the parameters over the maximized loss. In other words, for every outer minimization step we take, we have to do an inner maximization where we find the perturbation that maximizes the loss. So this makes adversarial training significantly more expensive than standard image classification training. I will go into a little bit more detail about this later on. So now hopefully we have a method in training our neural networks to satisfy this specification. How can we go about evaluating this? So now in this next section, I want to go over in a little bit more detail on the methodologies we used to do adversarial evaluation on finding the worst case. So the goal of the adversarial evaluation is really to find the worst case perturbation for each example in the test set. And once we have found this worst case perturbation, we now want to evaluate the accuracy of this new test set, where each example in the test set is now replaced with the worst case adversarial example. That is the original example plus the worst case adversarial perturbation. And this accuracy is known as the adversarial accuracy. But there are several complications, one of which is that to find this maximum exactly can be shown to be an NP-hard problem when your activation functions is ReLUs. And another complication comes in when we note that this is in fact a constrained optimization problem, because we want the delta to be constrained within the set capital B. So instead of trying to find this maximum exactly, rather what people try to do is they try to approximate this maximum with a form of gradient ascent. And because this is a constrained optimization problem, what we do is something called projected gradient ascent. So what projected gradient ascent is simply gradient ascent like this. But the moment we fall outside of the constraint, which is denoted by this yellow box here, we project this back onto the nearest point that satisfies the constraint. So mathematically, what this now looks like is the following. So I want to break this down a little bit. Firstly, we see that within this projection function, we have exactly gradient ascent, where you have your initial delta, and then you take a gradient with respect to delta in the direction to maximize the loss. And your step size here is denoted by eta. And once we have computed this update step, now we want to project this back onto the set that we care about. And more importantly, we project it onto a point which is the closest to the update. So this is the projected gradient ascent update step. And actually, one of the more popular forms of projected gradient ascent is the fast gradient sign method, while we're considering perturbations within the L infinity norm. So what the fast gradient sign method does is it tries to replaces the gradient, with the sign of the gradient instead. But actually, we can replace the gradient with any alterations made by any optimizer. So for example, we can replace this with maybe momentum optimization or atom optimization. So there are a lot of things for you to kind of try. The step size, the optimizer, the number of steps you want to take for your gradient ascent. And often you want to explore these parameters such that you get the strongest evaluation possible. So here at this point, I want to go on to something which I want to emphasize for a little bit. So I'm going to stay on this slide for just a few minutes. So what do I mean by a strong adversarial evaluation? Well, first of all, to see what I mean, we need to note that your adversarial accuracy is dependent on the many choices you make during evaluation. That is, it is dependent on the number of steps that you take for your projected gradient ascent, your step size, your optimizer, and many more. So the stronger your adversarial evaluation is, the lower your adversarial accuracy should be. And we should always be trying to evaluate our networks such that we obtain the lowest adversarial accuracy possible. The reason why this is because the lowest adversarial accuracy is the number which is closest to the true specification satisfaction. And that is the one thing we care about. So because of this importance, I thought I should give you a few heuristics of what I use to ensure that my adversarial evaluation is strong. So the first thing I kind of look at is the number of steps for the projected gradient ascent. It might not be surprising, but the more steps you take for your projected gradient ascent, the closer you are to maximizing your objective. That is, of course, conditioned on the fact that your step size is sufficiently small. The second one might be a slightly more subtle one, which is the number of random initializations for the perturbations. So what I mean by here is that firstly, you randomly initialize a perturbation before you start taking projected gradient ascent steps. So we want to actually have a number of different random initializations. This is especially important when it comes to detecting behavior called gradient obfuscation, which is something I will go into in a little bit more detail later on. Another factor which I also look at is the optimizer that is used. So this is just a good thing to try out a few different optimizers to ensure that you always get the lowest adversarial accuracy. And another factor which is also quite important for detecting gradient obfuscation is using a black box adversarial evaluation method. So what I mean by black box is when we assume that we're not given the weights of the network. So the adversarial evaluation, such as projected gradient ascent, is otherwise known as a white box adversarial evaluation because we are given the weights of the network. So the reason why I want to go into detail about why it is important to make sure your adversarial evaluation is strong is because we have seen the dangers of weak adversarial evaluation. So these are two papers published in 2018, where they have actually shown that weak adversarial evaluation can give you a very false sense of security. So what they did was they took a lot of the defenses published up until then, and then they tried their new strong adversarial evaluation on all of these defenses. And surprisingly, this stronger adversarial evaluation broke many of the defenses, causing their adversarial accuracy to go to zero. That is many apart from adversarial training, which is the one you see on this line. And this is possibly one of the many reasons why adversarial training is still heavily used today. Another benefit about stronger adversarial evaluation is that it actually gives you a true evaluation of progress. So I want to highlight this paper here because what I loved about this paper was that they did a large-scale evaluation of the defenses published up until then, and then they took the numbers, the adversarial accuracy, which was reported in their paper, and compared it to what they got under their evaluation. So this work is very cool in two senses. Firstly, they have evaluated all of these works under now a consistent set of adversarial evaluations. And secondly, as you can see by the drop in the adversarial accuracy for many, this set of adversarial accuracy is much, much stronger than what the others have used in the paper. So now you can see if we can use a stronger adversarial evaluation, that our adversarial accuracy for CFAR10 is not even above 60%. Whereas if we're just going to take the numbers that is reported in this paper as is, maybe we're going to be under the impression that is almost 70% and above. That's why it's extremely important for us to take care when we're doing adversarial evaluation. So another reason why strong adversarial evaluation is important is because training methods like adversarial training is prone to an effect called gradient obfuscation, something that I've mentioned a couple of times already. So here I will go into detail what gradient obfuscation is. And to describe what gradient obfuscation is, I want to go back to the training objective for adversarial training. So let's recall that the training objective for adversarial training has both an outer minimization step as well as an inner maximization step. And in this, I just want to focus on the inner maximization. So we can approximate this maximum similar to how we actually do adversarial evaluation by doing projected gradient ascent to approximate this maximum. However, we note that there is a little conundrum, which is that even though the more steps we take, we might be getting closer to maximizing the objective, but the more steps we take, we also make adversarial training significantly more expensive. So how can we make adversarial training cheaper? Well, maybe a naive way of doing this would be simply to do fewer steps of gradient ascent. For example, I can simply take maybe 2 steps of gradient ascent. But actually, what happens when you take too few steps to maximize the objective is that the network learns to cheat by making a highly nonlinear loss surface, such that simply by doing 2 steps of gradient ascent would not be even close to maximizing the objective you care about. So here is an example of a gradient obfuscated surface. So what you see on this plot here, the x and y axes is basically a hyperplane cut through image space, and we plot the loss at every single point in this hyperplane. And as you can see that this is a highly nonlinear behavior for this small region of image space. Whereas if you do adversarial training correctly, what you should actually expect is a much smoother looking loss surface. So with all of these dangers of weak evaluation and gradient obfuscation, it really pushed people into thinking about maybe a different way we can evaluate our algorithms. And this is called verification algorithms. So verification is very cool in the sense that it is able to find a provable guarantee that no attacks that has ever been invented or will ever be invented can succeed in changing the specification satisfaction of your network. So there are generally 2 types of verification algorithms. The first type is a complete verification algorithm. What these algorithms normally do is often an exhaustive proof. For example, using mixed integer programming, assuming that your activation functions is a ReLU. And often what they do is they either find a counterexample or they find a proof that the specification is satisfied. But unfortunately, these algorithms are very difficult to scale to deep neural networks. So rather, people use incomplete verification algorithms. So incomplete verification algorithms is similar to complete verification algorithms in the sense that once a proof can be found, it is also a provable guarantee that the specification is satisfied. But the difference is that a proof cannot always be found, even if your neural network satisfies the specification. So in other words, incomplete verification algorithms give you a lower bound on the specification satisfaction. So I want to go into a little bit of detail about these incomplete verification algorithms. Starting with this illustrative sketch of a neural network that takes in as an input X and gives you an output Y. So we generally make 2 assumptions for verification. The first one is we assume that the input comes from a bounded set, denoted by capital X here. And the second assumption we make is that our neural network consists of linear and activation layers. Please note that your convolutional layers can also be cast as a linear layer. So with these 2 assumptions, what we can now do is we can propagate the bounds of your input set through your linear and activation layers sequentially until we can get an output set denoted by capital Y here. And once we have this output set, we can simply see if it lies on one side of the decision boundary or not. However, the caveat here really is the true propagation, the exact propagation of these bounds is in fact NP-hard. So what incomplete verification algorithm instead tries to do is they try to find a more scalable way of propagating these bounds that is as tight as is possible to the true set that we actually care about. But what we kind of lose is that now, instead of getting the true set, we get an over-approximated set of the true set. So an example of such a bound propagation technique is that we can imagine if your input is lower and upper bounded, we can simply compute the lower and upper bound after linear transformation. And similarly, after that, we can compute the lower and upper bound after an activation layer. But the problem with these techniques is really that if your bound propagation is too loose, in the sense that the over-approximation is too big of an approximation of your true set, then your incomplete verification cannot mean very much. So what do I mean by this? Well, to see what I mean, first of all, we want to note that for incomplete verification algorithms, we only know the over-approximated set. So we have no idea what this true set is. So in the ideal case, if your over-approximated set lies on one side of the decision boundary, then indeed we have proven the true set lies on one side of the decision boundary as well. That is to say, we found that this satisfies the specification. However, if your over-approximated set is too large and it spans both sides of the decision boundary, then there is very little we can say about the set Y. Of course, we can try to close the gap on maybe distinguishing between these two cases by actually doing projected gradient ascent, like I've talked about before. And here is the graph which shows the difference of doing such an empirical adversarial evaluation compared to doing an incomplete verification algorithm. So what this graph is showing on the x-axis, you can picture this to be the size of your input set, capital X. And on the y-axis is the amount of specification violation. So remember, incomplete verification algorithms give you a lower bound on the specification satisfaction, thus gives you an upper bound on the specification violation. Whereas on the other hand, the empirical adversarial evaluation gives you a lower bound on that specification violation. So the true specification violation lies somewhere in between. If our bound propagation techniques for incomplete verification algorithms is tighter, the gaps between these two will be reduced. So there is more we can say about the true specification satisfaction of your neural network. But if your bound propagation techniques is too loose and the gaps of this becomes larger and larger, at some point there is very little we can say about the specification satisfaction. So today I've just touched on the adversarial robustness specification, but all of the techniques I've mentioned today can be used for many other specifications. For example, we can consider semantic consistency for an image classifier. That is, maybe some mistakes are more catastrophic than others. For example, for a self-driving car, it might be okay to mistake a cat for a dog because ultimately it doesn't change the driving policy very much, but it is not okay to mistake it for a car. Or for a dynamical systems predictor, we can be looking at laws of physics, such as energy conservation. So hopefully what I have done today is giving you a rough outline on how you can train your neural networks to satisfy specifications, and more importantly, evaluate how much your neural network satisfies these specifications. But more importantly, I very much hope I have motivated everyone into thinking why looking into this is important. And this concludes the end of my talk. And now I want to pass on to Yason, who will give you a more detailed overview of the ethical implications of machine learning algorithms, and more importantly, how we can be thinking about deploying and designing these algorithms to be beneficial to society.
I'd like to start by thanking Chong-Li for her fantastic exposition of some of the key challenges that arise when building algorithms that are safe, robust, and fair. In this section of the talk, we'll focus more directly on the question of responsibility and what it means to deploy these technologies successfully in real-world settings. However, before we get started, I'd like to reintroduce myself quickly. My name is Yasun Gabriel, and I've been working at DeepMind as a research scientist in the ethics research team for 3 years. Before joining DeepMind, I used to teach at a university where my work centered on moral philosophy and practical ethics, including questions about global poverty and human rights. At DeepMind, our team explores questions that arise in the context of ethics and artificial intelligence, some of which we'll look at in the course of the next hour. So, if we begin with the topic of ethics and machine learning, we immediately encounter questions including what is ethics and why does it matter, and how does ethics connect with machine learning? I'd like to take these questions in turn. Ethics is a field of inquiry that's concerned with identifying the right course of action, or with what we ought to do. It's centrally concerned with the equal value and importance of human life and with understanding what it means to live well, in a way that does not harm other human beings, sentient life, or the natural world. According to our everyday judgment, some actions are good, some are acceptable, and some are prohibited altogether. Understood in this sense, ethics is interested in identifying what we owe to each other and how we ought to act, even in challenging situations. These situations can arise in our personal or professional lives. However, they also arise in the context of machine learning research. What I'd like to suggest is that far from being outside the domain of ethical evaluation, technologists and researchers are making ethical choices all the time, and many of these choices deserve closer consideration. As Chongli noted, a good place to start is with the training data we use to build machine learning systems. In particular, we need to appreciate that data is not only a resource, but also something that has ethical properties and raises ethical questions. For example, has the data been collected with the consent of those who are represented? We cannot take this for granted. Of course, there's high-profile cases of data being collected without people's consent, such as Cambridge Analytica, but it's also a common challenge for major datasets used to train image recognition systems that often use pictures of celebrities or simply images taken from the internet. Second, who or what is represented in the data? Is the data sufficiently diverse, or does it focus on certain groups to the detriment of others? If we train a model on this data, will it perform well for people of different genders, nationalities, or ethnic backgrounds? Or might it fail when applied to these groups in significant ways? Thirdly, how is the data labeled and curated? Does it contain prejudicial associations? As Kate Crawford and Trevor Paglen have demonstrated in their work on excavating artificial intelligence, in the early days of ImageNet, it contained a persons class that assigned pejorative labels to a variety of images of real people. This is also a problem for historical data that's drawn from specific social contexts. Regardless of how that data is labeled, it may contain associations that are a reflection of human prejudice and discrimination. These challenges, which arise early on in the machine learning pipeline, have come to have a real-world impact, a phenomenon that's most commonly referred to by researchers as the problem of algorithmic bias. Indeed, while these technologies have great potential, recent evidence suggests that far from making things better, software used to make decisions and allocate opportunities has often mirrored the values and biases of its creators, extending discrimination into new domains. These include the domain of criminal justice, where a program used for parole decisions mistakenly identified more Black defendants as high risk than people in other racial categories, compounding entrenched patterns of racial discrimination within the criminal justice system. It's also been seen with job search tools, which have been shown to offer highly paid jobs or advertisements for highly paid jobs to men over women by a significant margin, sometimes by a ratio of up to 6:1. It's also a problem that's been noted for image recognition software, which has been shown to work less well for minorities and disadvantaged groups. And lastly, it's been something that we've encountered in the domain of medical tools and services, which have been shown to perform markedly worse for people with intersectional identities, something that could mean that they have unequal access to life-saving services and medication. Faced with this mounting body of evidence, we cannot rely on good intentions alone. There is clearly an important body of work to be undertaken to address these failings. It is also clear, to return to a point that Chong-Li made earlier, that those who design and develop these technologies are in a position of power. So what is power? In this context, I think it's best understood as the ability to influence states of affairs, and more importantly, to shape the lives of other people. More precisely, those who develop new technologies shape the world, creating new opportunities, foreclosing others, and shaping the path that humanity is likely to take. This can be seen with major inventions throughout history, such as the steam engine or electricity. Artificial intelligence is now also starting to have profound effects, some of them positive and some of them more challenging. With this power comes responsibility. However, the question then arises, responsibility to what? Chong-Li has already shown us what is possible from a research perspective. Clearly, there are certain things that we can do and that we may well be required to do when building ML systems. However, I'd like to focus on the question of responsibility and see if we can develop our understanding of what is required a little further. At a collective level, I believe that an understanding of the relationship between power and responsibility should lead us to reflect more deeply on the question of what it means to do machine learning well. After all, the activity of scientific research is not value neutral. Rather, it is a social practice that human beings engage in that's governed by shared norms that change over time. Some of these norms are epistemic, for example, ideas about the need for replication in order to confirm scientific findings. Others are normative or moral, for example, about the acceptability of doing research on people without their consent. Ultimately, with the way we structure this practice, including the way we think about what it means to do good research, has profound social effects. These questions about appropriate norms and standards for research are particularly important when the stakes are high and when there's uncertainty about the overall impact. In response to the unique challenges posed by nanotechnology, governments and civil society groups came together to develop a shared understanding of what they term responsible innovation. These groups characterize responsible innovation as a transparent and iterative process by which societal actors and technologists become mutually responsive to each other's needs to ensure the ethical and social value of the scientific endeavor. This paradigm points towards the important idea that good science is itself based upon alignment with the social good and with democratic processes, a point that I'll return to later on. At the same time, the paradigm has been criticized for its vagueness. What precisely are researchers responsible for? What should they do, and how does this apply to the realm of machine learning? These are questions that I shall now try to answer more concretely as we turn to principles and processes for thinking about the ethics of artificial intelligence. So as AI researchers, I believe that we share in responsibility for at least two things. First, we are responsible for intrinsic features of this technology, so that we build the very best systems that are sensitive to ethical and social considerations and are designed in ways that limit the risk of harm. Secondly, we bear some responsibility for extrinsic factors that help determine whether it's designed, deployed, and used wisely in ways that produce beneficial outcomes. Both elements are necessary. Robust and secure technologies can be used in harmful ways by bad actors, and faulty technologies can be problematic even if they're deployed and used responsibly. In terms of the content of these obligations, what I've termed the responsibility for what question, there are now a multitude of AI principles that, broadly speaking, aim to align machine learning research and systems with the social good. This includes offerings by the European Union, the OECD, the Beijing Academy of AI, and by the Future of Life Institute. Indeed, one recent study found that there's at least 84 different ethical codes that have been proposed for AI. Fortunately, these principles coalesce around certain key themes, such as fairness, privacy, transparency, and non-malfeasance. The last condition, which is sometimes characterized as do no harm, leads us to focus on the affirmation of individual rights. This includes things like respecting the requirement for informed consent and equal recognition before the law. Lastly, I believe we should try and develop artificial intelligence in ways that satisfy the collective claim to benefit from scientific discovery. Interestingly, this is also found in the United Nations Declaration on Human Rights, which establishes a right of all humanity to share in scientific advancement and its benefits. Yet, even with this understanding of the key values in place, certain gaps appear to remain. First and foremost, how do we move from these statements of principle to clear and robust processes for evaluation? We know that good intentions are not enough, but how do we take abstract moral ideals and turn them into these concrete processes and procedures? How should we balance and weigh different ethical principles against each other? And how should we deal with the fact that machine learning research is often highly theoretical and general, meaning that there's uncertainty about how it will ultimately be used? One answer is that we need tools that help us put principles into practice. In what follows, I describe a 5-step process that technologists can use to evaluate our research and help make sure that it's ethically and socially aligned. While this process does not aim to capture the entirety of AI ethics, my hope is that it can be of use to many of us who are doing practical work designing and building algorithms. This framework is particularly helpful in relation to the values previously discussed. I will now run through the process briefly and then return to consider each stage in more detail. So the first question we need to think about when building new technologies is whether it has a socially beneficial use. Is there actually a reason to develop the thing that we want to develop? Now, most technologies do have socially beneficial uses of one kind or another. But if we're unclear about what the value is that we aim to unlock, that's typically a red flag that should immediately force us to go back and reconsider what it is that we want to do. By getting this social purpose clear in our minds, it's also often true that we can create better versions of the technology that we had in mind. But once we have this social purpose in mind, we then need to turn to think about the risk of direct or indirect harm that the project brings with it. So here again, it's typically true that most technologies bring with them some risk of harm. And the important thing is to try and map out these risks clearly, so we know what we're contending with at every juncture. Then, with an idea of what the benefit is and the risks that the project brings with it, we should turn to think about mitigation. Are there steps we can put in place that will reduce the risk or eliminate risks entirely? Then, with this plan in place, we can finally turn to the first evaluative stage. So now we have the best version of the technology or piece of research in mind, and we can ask, with these measures in place, does the proposed action or research violate a red line or a moral constraint? Does it push up against some threshold or barrier, which comprises the sort of things that we just ought not to do? Finally, on the assumption that we haven't hit one of these hard constraints, we have the question of whether the benefits outweigh the risks from an ethical point of view. And at this point, it's often sensible not just to focus on the specific project at hand, but also to consider other options that are available to us. Given that we've been afforded this opportunity to do research, is this really one that looks like it will add value to the world? Okay, so now we'll take a moment to look at these questions in more detail. So what is a socially beneficial use of technology? What does this mean? Well, I think that a technology can be socially beneficial in a variety of ways. To start with, it could contribute to human health or well-being. So it could make us physically more healthy or better off in some way. Technology could also enhance our autonomy or freedom. if it empowered us to act in a way that fulfills our own goals or outcomes. For example, by giving us useful information or by helping us be more discerning when it comes to understanding the world around us. Technologies can also help produce fairer outcomes if they're well designed and calibrated and developed in a way that includes the voices of people who are affected. They can contribute to public institutions such as healthcare or education, and these systems can be used to address global challenges such as climate change. Of course, there's certain gold standard research for ethically impactful work, such as medicine or work to address climate change. But it's also okay to focus on more prosaic goals and aspirations. For example, to try and create technology that brings people enjoyment or gives them more time to do other things. If we take an example, a technology developed by DeepMind, which was WaveNet, an algorithm that we created to help produce better quality synthetic audio, I'd say that one of the socially beneficial uses of that was to help visually impaired or illiterate people access digital services more effectively through voice interactions. Secondly, we then have to consider this question of harm. So what sort of things fall into this category? Well, here, what we see is that the harms are often the inverse of the benefits that we might try and unlock. So instead of improving human health or well-being, technology might undermine human health or well-being, including potentially mental health. It might restrict human freedom or autonomy, something that comes to the fore if we think about the challenge posed by addictive content. It might lead to unfair treatment or outcomes, as we saw in the case of algorithmic bias. It might harm public institutions or civic culture, and it might infringe human rights. So if this is the case, it's something that we really would need to be mindful of. Returning again to the case of WaveNet, we understood that that research carried with it certain risks, including voice mimicry and deception, if individuals used it to copy each other's voices. And it could also potentially erode public trust in the fidelity of audio recordings. So once you have an understanding of these risks, the question is, what can you do about them? Is it possible to mitigate these risks or to eliminate them entirely? And in that regard, there's a number of significant things we can think about. The first is whether it's possible to control the release of technologies or the flow of information. So often technologies only have harmful outcomes if they fall into the hands of people who have a malicious intention or purpose. And we need to think about whether there's ways to prevent that from happening. We might also wonder if there's technical solutions and countermeasures that we can use to make our technology harder to misuse, something that Chong-Li really delved into. And in the context of WaveNet, we can think about things like watermarking, so that we always know the progeny of a specific piece of synthetic audio, or detection. We also have the opportunity to work with public organizations and the public to communicate certain messages around technology. So sometimes if a new risk is being created, it's very important to make people aware of this, although that often isn't sufficient to discharge our moral responsibility. So finally, we may seek out policy solutions and legal frameworks that help contain the risk. And in the case of the challenges raised by synthetic media, civil society groups have been really, really important in terms of coming up with a united agenda that helps make sure that these technologies are used in a safe and responsible way. So once we have our mitigation plan in place, we have this question of whether the proposed action violates a red line or moral constraint. These constraints are sometimes referred to in moral philosophy as deontology. They're made up of a set of rights and duties that mark out the sorts of things that we should not do. For example, it would be deeply problematic to develop technologies that contravene consent protocols that infringe on people's personal space in ways that they haven't consented to. Similarly, in the domain of artificial intelligence, there's a concern about lethal autonomous weapons and what happens when human decision makers delegate these fundamental decisions to machines. So there's an international movement which has also developed around legislating in this area and containing that risk. and ensuring that this technology isn't used in a way that intentionally harms or injures human beings. Thirdly, we might be concerned about certain forms of surveillance that also could have a corroding effect on public trust and lead to people who are being victimized and targeted in certain situations. So that would be a really important avenue to be mindful of. And then we have technologies that potentially infringe human rights or international law. And basically, if there's any risk that the technology will be used in a way that contravenes one of these fundamental purposes or one of these fundamental principles, that again is a red flag, which really should encourage us just to go back to the drawing board and ask the earlier question: what does a safe, beneficial, and productive version of this technology look like? However, on the assumption that we haven't encountered one of those hard constraints, we still have this final question, which is, with these measures in place, do the benefits of proceeding outweigh the risks of doing so? And as I mentioned earlier, when we think about machine learning research, it's a tremendous opportunity to do something really beneficial. And we've actually been afforded a great opportunity, typically by universities, by research institutions, to try and use our talents in a way that's genuinely helpful. So we should ask, is this project something that we really feel will deliver the kind of social return that we care about and that has the potential to make people better off in practice? However, even when we've got through this process and come to the conclusion that we have got a good way of proceeding, it's still worth pausing to evaluate our findings and to conduct 2 further tests. These tests are particularly helpful because they can help us address the problem of motivated cognition, i.e. the widespread problem of unconsciously endorsing arguments that support our own interests or our preferred course of action. So first, I'd ask, have you thought about all the people who could be affected by your action? More precisely, have you identified these groups? Do you know who they are? Have you considered what would happen if you were trying to explain your reasoning or your decision to them? And have you directly sought out their advice and input? This test is important for a number of reasons. To begin with, those who are affected by new technologies typically have a right to be included in decisions that affect them. Moreover, even a process of imaginary and sympathetic dialogue can help us guard against error. If we'd really struggle to explain our actions to someone who is adversely affected by technology, then this is often a good reason to revisit our conclusions and work hard to identify a solution that could pass that test. Secondly, I think we should ask whether we've thought seriously about how our decision might be viewed in the future. Is it something that we might have reason to regret? Here we can imagine someone in the future, perhaps even our own children or grandchildren, asking us why we chose to act in the way we did. Why, for example, did we fly to so many conferences when we knew about climate change and the harmful impact we were having? How might it feel if we were to discover that our technology was subsequently used in a way that violated human rights? If these questions make us feel uncomfortable, then we have reason to introspect and identify that source of discomfort. Moreover, we should typically adjust our behavior to act in ways that minimize the likelihood of future justified regret. So now we've had a chance to look at the responsibilities of machine learning researchers and at a process for evaluating our decisions and choices. However, it's also worth pausing to reconsider where we are now as a field and what the path ahead might look like. The field of machine learning is changing rapidly, both in terms of technical developments and breakthroughs, and also in terms of ethical norms and standards. Increasingly, I believe there's recognition of the following key ideas. First, those who design and develop these technologies have a responsibility to think about how it will be used. This responsibility stems from the fact that the technology is powerful and from the fact that it has moral consequences that we can observe and that we're in a position to affect. Secondly, there are concrete steps and processes that we can put in place to make sure that this responsibility is successfully discharged. These include processes like the ones we've considered today that help promote the good while also respecting important constraints. Thirdly, while it's not possible to know the consequences of all our actions, we are responsible for what we can reasonably foresee and should take steps that are designed to bring about positive outcomes, even when this means incurring certain costs. Given the power of machine learning technology and the attendant responsibilities of people working in this field, good intentions are not enough. We have an obligation to try and understand the impact that our actions will have on other people and to act conscientiously in light of that information. Beyond this, we can pause and ask about the path ahead. So in this regard, I see three exciting developments that we are all part of at the present moment. So to start with, there's an important new research agenda that's developing in this space and includes a critical focus on areas such as AI safety, robustness, fairness, and accountability. This technical work to improve the moral properties of machine learning systems requires constant vigilance and effort. But as Chong-Li has shown us, there are things that we can do and that we can change to build better machine learning systems. Secondly, we're starting to see the emergence of new norms and standards that point towards a different understanding of what it means to do machine learning well. On this view, what is needed is not only technical excellence, but also for research to be done in the right way and for the right reasons, limiting the risk of harm while also working to create technologies that benefit everyone. Finally, we're seeing the emergence of new practices which aim to promote responsible innovation in machine learning. These include the release of model cards that explain the intended uses and properties of ML systems, a proposal from top research labs to create bias bounties aimed at discovering bias in models and datasets that we use, and a new requirement from the Machine Learning Conference NeurIPS, which asks all researchers to consider the ethics and social impact of their submissions and to detail this when we write papers. While very significant challenges still remain, I think that these developments send a good sign towards the future. With the requisite degree of effort, reflection, and conscientious endeavor, they will help ensure that machine learning as a field stays on the right track and continues to be an area of study that we can all be proud of. Thank you.